In part one, we talked about related rates. It was a pretty long video because we were just learning them and it's kind of a tough topic. For part two, it's going to be a much shorter video because basically for today's assignment, you're just going to get some extra practice on related rates, but I wanted to focus on one very important question. So in part one of the things we talked about was the difference when you're labeling your variables or your rates, the difference between something that's constant and something that's changing and has to be assigned a variable. So the important question I want to talk to you guys about today is the difference between a cone and a cylinder. These are real common AP test questions, and they're also common mistakes on the AP test. So I want to make sure you guys know this really well and don't make those mistakes. So yesterday in class, or not yesterday, in part one, we did this question where we had a cylinder like this, and the cylinder was filling up with water. And what we were doing was basically measuring the volume of water, that smaller cylinder inside of it. Now in the question, I gave you the radius. I think it was 5. I said R equals 5. Now in a cylinder, when you're measuring the volume of water, remember you're actually not measuring the volume of the whole cylinder itself. You're measuring the volume of the blue cylinder, the one inside of it. But it didn't matter because the radius is 5 no matter where you are in the cylinder. So basically R was constant and we just plugged 5 in our answer. Now in just a minute, we're going to do basically the exact same question, but instead of a cylinder, it's going to be a cone filling up with water. And here's the difference. Let's say the cone has the same radius. Radius equals 5. But see, it's not constant anymore, because if I measure the radius on that tiny blue cylinder in there, it's definitely less than 5. We actually don't know what it is. Depends on how high the water is. The higher the water is, the bigger the radius gets. So in that case, the radius is a variable, and you can't just plug 5 in for it. You need to either eliminate R or be able to plug in a rate for it. So let's go ahead and do our only example for today. You guys will notice it's very, very similar to yesterday's. I copied and pasted yesterday's. I changed cylindrical to conical. I changed the formula, even though all I did was add a 1/3 into it. Hopefully you guys noticed the formulas for volume of a cone and a cylinder are exactly the same, except a cone has 1/3 the amount of a cylinder. So yesterday our formula was pi r squared h. Today it's 1/3 pi r squared h. All right, so anyways, we have the same concept. We have that, this time it's a cone. Conical means cone-shaped. So we have a cone-shaped tank. Radius is 5 feet, height is 10 feet, and water is pouring into it at a rate of 10 cubic feet per minute. Same setup as yesterday. And I said, how fast is the water level rising when the water level is 3 feet? All right, so let's start with a picture. Here is my cone. It's going to be the same one I just drew on the last slide. And I said the radius is 5, and the height of that cone is 10. Now, there's some water in it, so let's put some water in it again. And see how when I put that water in there, what it makes is a smaller cone inside of the bigger cone. And we're measuring the volume of that smaller cone, how much water is actually in there. Now what we have in this problem is 2 variables, because as water pours in here, the water level, I'm going to call it h for height, the water level rises. So the height of that smaller cone is increasing. And like we talked about on the other slide, the radius of that cone is also changing. So we actually have 3 variables: volume, rate, and height. So I got my picture. I got my my variables assigned. The next step, the next important step that we said for related rates question is to find the rates. So what I have here, if I look for rates, number 1, 10 cubic feet per minute. That's definitely a rate, and remember you can tell by the units, cubic feet per minute. And in fact, it's going to be dV dt because it's in cubic feet. So dV dt equals 10. Now, the water is flowing in, so it's positive 10. You always want to check for that. If water was leaking out of this cone, it would be negative 10. And it asks us, how fast is the water level rising? Well, that's h. So we are being asked to find dH dt. That's the rate part there. Let me kind of circle that off. So those are the only rates in the question. I was given one and asked to find dH dt, asked to find another. So what I need is an equation that relates V and H. Now I gave you the equation. It's right there in parentheses. It's volume equals 1/3 pi r squared h. Now the problem is, and this is another thing I mentioned in the notes in part 1, but we didn't see an example of yet, there's an extra variable in there. I need an equation that relates V and H only, so I can't have that R in there. Now with the cone, it was very easy to get rid of R. I'm sorry, with the cylinder, it was very easy to get rid of R because it was constant. We just plugged a number in. You cannot do that on this question. If you plug 5 in for R right now, then what you're doing is you're telling the formula that R is constant, and you're telling the problem that it's a cylinder and not a cone, and you would get the wrong answer. So you cannot just plug in 5 this time. We need a different way to eliminate it. Now the way you're going to eliminate it is actually realizing, let's look back at our picture. The two cones that you see there, the original big white cone itself, and the smaller one inside of it that's actually the shape of the water, those are similar. They're similar shapes and they're proportional. So if I set up a proportion out of the radius and the height of each one, then what I can do, and you'll see how this goes. So let's set up a ratio for the big cone. The ratio for the big cone would be the height is 10 and the radius is 5. Now the ratio for the small cone, the height is h and the radius is r. So what I did is I used proportions, I used similar shapes. I just did height over radius for the big one equals height over radius for the small one. Now, if you cross multiply, which you can do with a ratio, you get 10r equals 5h. Now remember, my whole goal of doing this, the whole reason I did this is I want to get rid of this r right here. So what I want to do is solve for r. Let's divide both sides by 10 and reduce, and r ends up equaling h over 2. So let's make that substitution. If r equals h over 2, let's just change it into h over 2. So what I get now is v equals 1/3 pi times h over 2 squared times another h. And now let's clean that one up a little. If I square the h over 2, I get h squared over 4. And if I combine everything, I get 1/12. If I multiply the 3 and the 4, I still have the pi, and then I get h cubed. So what I have now is exactly what I needed the whole time. I have a formula that relates v and h only. Now once you have that, take the derivative with respect to t. This is the implicit part. So I take the derivative of v and I get dv dt. For the other one, now remember the 1/12 pi, that's your constant. So just leave that and do the power rule on the h cubed. So I'm going to multiply by 3. 3 over 12 would reduce to 1/4 pi. We'll lower the exponent by 1 to h squared, and then we'll have a dH dt. And now, if we plug in our numbers, we should be able to finish the question at this point. So I think I'm going to erase my work on the right over there just to give us a little space. All right, So I'm going to use that red equation. I'm going to plug in 10 for dv dt. I have 1/4 pi. Maybe I'll just call that pi over 4. That's actually a little easier. Now, it says we have h squared. Now, we haven't actually used it yet, but remember in the question, I said, how fast is the water level rising when the water level is 3 feet? That's when you're going to finally use that. That's what that extra piece of information was for. You need it at the very end to plug in. And then that is times dh dt. So what I get is 3 squared would be 9, so I would have 10 equals, that would end up being 9 pi over 4 dh dt. And then to finish solving, if I want to cancel out a 9 pi over 4, I'm going to multiply by reciprocals. I'm going to multiply by 4 over 9 pi to cancel that. And for my final answer, dh dt ends up being 40 over 9 pi. And that would be in, let's see, it's height, so that would be in feet per minute. Now that was very similar to the example we did in class in part 1. But basically the difference, and the very important difference, this was a much harder question. In part 1, because it was a cylinder, once I realized I needed to eliminate this r, I basically just plugged 5 in and squared it. And then I was already ready to take the derivative. I got to skip all that work in green, and the work that I erased to make extra space. So you got to make sure, the point of today's notes, the point of today's video, is to remind you guys to be very careful on this problem. If something is changing in the question, and you put a number in for it, you put a constant, then you won't get the right answer. So be very, very careful when you're doing these questions. Pay very close to attention to what is changing in the question, that has to be a variable, and what is not changing, that is a constant.